useful. Okay. So firstly, we need to prove the integrability of the linear combination. Firstly, we consider the case that both A and B are non-negative. Why we need to consider non-negative case? Because our argument will involve some inequality. If you multiply a negative number to the inequality, the inequality will reverse its direction. So this will cause some inconvenience. Therefore, we consider the non-negative case first. Okay. Then we want to prove that the linear combination is integrable. So we take any partition of the rectangle I, that is P. So for every subrectangle in this partition, we have the following result. AMJF plus BMJG will not greater than AFX plus BGX for every x in the subrectangle J. This is quite obvious, okay? Because MJF is the infiniment of x. Is the infiniment of f over J. Therefore, for every x in J, MJF will not greater than fx. Similarly, MJG will not greater than gx. Okay? So, because A and B are non-negative, so we have this inequality. So, this inequality is true for every x in J. Therefore, the left hand side does not depend on x, but the right hand side. So we can let x change and take the infiniment of the right hand side. Then the right hand side will become the infiniment of the linear combination over J, and the left hand side does not change. Therefore, we get this result. Here, MJ alpha f plus BG is the infiniment of the linear combination of f and g over the rectangle J. So we have this inequality. Then we multiplying both sides by the volume of J, and then sum up. We obtained this term multiplying the volume of J and the sum up will give us the lower sum of f, which is vector partition P, and this term give us the lower sum of G, and the right hand side is the lower sum of the linear combination. So we have this inequality. Okay. Now, given epsilon positive, because f and g are integrable, we can take two partitions of I, so that the lower sum of f with respect to the partition P1 is very close to the integral of f over I. Okay. No, we have not used the integrability here. Yes, we use, the lower sum can be approached, the lower sum can approach the lower integral, but because the function is integrable, the lower integral is actually the integral of f over I itself. So for a suitable partition P1, the lower integral, that is the integral, subtract the lower sum will not less than epsilon, or will less than epsilon, because the lower sum and the lower integral will be very close. Okay, therefore we can write the result in this way. Similarly, by the integrability of G, we can get another partition of I, that is P2, such that the integral of G is close. The lower sum of G with respect to this partition is close to the integral of G, which L epsilon. Okay. So as before, once we have two partitions, we will consider the common refinement of these two partitions. So we denote this by P minus. That is the common refinement of P1 and P2. Then our previous result can be written in this way. F minus G, the integral of F minus epsilon will not greater than the LF P1. Similarly, the integral of g minus epsilon will not greater than LGP2. And because AB are non-negative, so we can multiply the AB to obtain this inequality. Maybe here we should use not greater than, because if A and B are all 0, then both sides of this are 0. Therefore, this is equal, not strictly less than. Okay, so this should be less than or equal to. Okay, now we're using this result. For the common refinement, we have this inequality, and then we will compare the lower sum of f with respect to p1 and g with respect to p2 to the lower sum with respect to the common refinement. So we have this inequality because p minus is the refinement of p1. Therefore, the lower sum of f with respect to p1 will not greater than the lower sum with respect to p minus. And similarly for the lower sum of g, we have the same result. Therefore, we get this inequality. And the lower sum will never greater than the lower integral, because the lower integral is the supplement of lower sum. So we can, I forgot. So here we use the previous inequality here. Okay. So this can be written by the lower sum of the linear combination, and then lower sum will never greater than the lower integral. No, we don't use that. We stopped here for the discussion of lower sum of the linear combination of f and g. And using similar argument, we can obtain the upper sum of the linear combination. So we will obtain this inequality. So we decrease the integral of f and g slightly, and then make a linear combination will be controlled by the lower sum of the linear combination. And for upper sum, we increase the integral of f and g slightly, and then we will have this inequality. So combine these two inequality, we will obtain because this is with respect to different partition. The capital F and how to say, we want to establish the integrability of alpha AF plus BG. So we need to prove that for some partition, the difference of the upper sum and the lower sum of the linear combination AF plus BG is very small. This will give us the integrability of the linear combination. So we need to make the partition the same partition. You have P minus and P plus here. Okay, so we need to transform this into the same partition. How to do this? Obviously, we take the common refinement. So we let P to be the common refinement of P minus and P plus. Then we copy our previous result. We copy this inequality, decrease the integrals of f and g slightly, and make linear combination will be controlled by the lower sum of the linear combination with respect to p minus. Okay, so we copy the argument. This is the inequality we obtained before. But because the p here is the refinement of p minus. It is the common refinement of p minus and p plus. Therefore, it is a refinement for both p minus and p plus. So, using the property of lower sum, if you refine the partition, the lower sum will increase. Therefore, this will not greater than the lower sum with respect to p. And the lower sum is always not greater than the upper sum. And when in refining the partition, the upper sum decrease, and the P is a refinement of P plus. Therefore, this upper sum will not greater than the upper sum which respect to P plus. Okay. Then for the P plus, we use the previous inequality. For the P plus, we have this inequality. Okay. So using this inequality here, we get this result. And we can. This means that for the partition P, the upper sum and the lower sum of the linear combination lies between the two ends of this inequality. Therefore, their difference, capital U subtract capital L, will not greater than the difference of the two ends of this inequality. That is, this will not greater than this subtract the right hand side subtract the left hand side. So the integrals are cancelled because you have A integral of f, B integral of g. The left hand side also have A integral of f and a B integral of g. So the integrals are disappears, but the epsilon term remains. So we have A epsilon plus B epsilon. The left hand side is minus A epsilon and minus B epsilon. Therefore, moving to the right hand side will give you 2A plus B epsilon. So this means for any epsilon positive, you can find a partition of the rectangle I such that the upper sum and the difference of the upper sum and the lower sum of the linear combination which respect to the partition P is controlled by a small number. Okay, so this proves that the linear combination is integrable. Okay, then we also need to obtain the integral of the linear combination. So our previous result we can copy. How to copy this? Here, why we have this inequality? Because the integral of the linear combination is greater than the lower sum. Okay, so from this inequality, the left hand side will keep unchanged, and the right hand side of this line will not greater than the integral of AF plus BG, and the integral will not greater than the upper sum. We mentioned the integral when the function is integrable, the integral is always lies between upper sum and the lower sum. Okay, so using this result, we have this inequality. This integral of AF plus BG will lies between these two numbers. So we can copy this inequality for getting everything in between, replacing by the integral, because this integral lies between these two numbers. Okay, so we have this inequality. So from this inequality, let epsilon goes to 0. Let epsilon goes to 0. The left hand side is A multiply the integral of f plus B multiply the integral of g, and this is also the right hand side. Therefore, both left hand side and right hand side converge to the same number. So it must equal the number in the middle. This is our equality. Okay, this is our equality. But until now we only proved the case for non-negative A and B. So you need to delve into the case that A or B might be negative. Okay, for the negative case, it is easy to see that you only need to study minus f. That is, B is 0 and A is minus 1. If the minus f is clear, then you can using the minus f to transform the A or B negative case to to the positive case, because if A is negative, AF is minus, is the absolute value of A multiplying by the minus F. So you can apply the result to minus F. Therefore, we wanted to prove that when F is integrable, then minus F is also integrable, and the integral of minus F equals equals to minus the integral of F. So the idea for proving this result is similar to the case we just to the previous case by linear combination, and actually it will be more simpler because you only need to consider one function. You only consider f no g here, so this will be easier using the set argument. So I will omit the argument here, and in the proof of this result, we will need the following basic observation. That is, the infiniment of minus f over a subrectangle is precisely the minus the supplement of f over that rectangle. And similarly, the supplement of minus f over g is minus the infiniment of f over g. Okay, so I will stop here. Thank you.